Thank you. So our first speaker is Tom Banks from Santa Cruz and Rutgers, and he will talk about the critique of pure string theory.
Thank you. I'd like to thank the organizers for inviting me and particularly for not rescinding the invitation. Hello? Can you hear me? Okay. So I'd like to thank the organizers for inviting me and particularly for not rescinding the invitation when they saw the title of my talk. I'd like to talk today about some conventional wisdom in string theory. I think the developments of the last year taught us that there are indeed supersymmetric theories of quantum gravity. M theory I think of as a set of moduli spaces, mostly of supersymmetric Poincare or anti-de Sitter invariant theories of quantum gravity. And I think the most attractive way of saying what we've learned is that if you put together the principles of quantum mechanics, supersymmetry, and gravity, or if you have enough supersymmetry, gravity is actually implied, that using what we call the BPS argument, or BPS arguments, you can prove that these moduli spaces exist and that they're continuously connected to weakly coupled string theory. And so string theory really follows from the principles of supersymmetry plus quantum mechanics. Now, in our conventional wisdom, we think of these different separated moduli spaces, the things that are not continuously connected, as still vacua of a single quantum mechanical Hamiltonian. And it's this view that I'm going to challenge in the talk today. So to do that, I want to go back to sort of the very beginnings of what we mean by a vacuum state and think about what the definition of a quantum theory is. So the clearest way of seeing that is to think about the Feynman path integral approach first, in which one sees very clearly that you define quantum mechanics by thinking about the propagation over very, very short times, or what is the same thing, thinking about the very, very high energy spectrum of the Hamiltonian. And the fundamental principle of the path integral formulation is that at very, very short times, the theory becomes free. It becomes a Gaussian model, a quadratic soluble Hamiltonian, and we can think of the interaction as a very small perturbation about that. And then that gives you the path integral formula for the entire theory, starting from that soluble free theory, using the variables defined by that soluble free theory. And that's really the basis of what we call canonical quantization and classical mechanics. We usually teach quantum mechanics the other way around, but I think this is the right way to think about it. More generally, we learned from Ken Wilson, in studying quantum field theory, this paradigm doesn't work exactly, but it's replaced by something similar. You again go to very, very high energies, and you ask what the behavior of the theory is at very, very high energies. And in quantum field theory, that turns out to be the same thing as asking what happens at very, very short distances. And then Wilson taught us that what happens at very short distances, generically, is a conformally invariant fixed point theory. And we can think about the proper definition of the theory as taking that conformally invariant fixed point and perturbing it by relevant operators. So the definition of a vacuum of the theory is a representation of that operator algebra. You look at the Green's functions of the theory, and they're basically determined by looking at the first few terms of the operator product expansion to determine what the fixed point is and what the relevant operators that are perturbing it are. And then different vacuum states are different representations of that algebra in Hilbert spaces that are separated from each other by superselection rules. And what goes basically into this definition is a split that exists in quantum field theory between the infrared behavior of the theory and the ultraviolet behavior of the theory. The ultraviolet behavior of the theory is local. It doesn't care about the boundary conditions, doesn't care about the global structure of space. And then thinking about that ultraviolet definition of the theory, we find different infrared ways of realizing it, which all have the same ultraviolet behavior. And that's really what we mean by a vacuum state in quantum field theory, and that's really the psychological basis for the paradigm we've been thinking about in thinking about string theory and quantum gravity. And it depends very much on this UVIR separation that appears in local field theory. Or one other point that's important, another way of thinking about this is to think about putting the theory in a box and putting different boundary conditions on the boundary of the box to separate out the different vacuum states, and then taking the volume to infinity limit to get the different vacuum states for the same Hamiltonian. You can do that again because the Hamiltonian is local. Now, another way in field theory of thinking about finding one vacuum state, if you know about another one, is to actually, again using locality, make a bubble of vacuum state number 1 inside of vacuum state number 2. You're living in vacuum state number 2, that goes out to infinity. And then if you're willing to expend enough energy, you can make a bubble of arbitrarily large size r, which looks like the first vacuum state. And you can do, because you can make r very large, and it takes a finite time for that bubble to collapse by causality, and you can make r as large as you want, you can do experiments in vacuum state number 1 that with arbitrary precision can determine the behavior of the vacuum in vacuum state number 2. So those are the ways that we have of thinking about vacuum states in field theory. So is this the right way to think about things? And I think the first clue that it's not comes from thinking about, again, what's the definition of a quantum theory? You go to high energies. So what's the high energy behavior of quantum gravity? And this is something that I discussed in collaboration with Ofer Aharoni and Willy Fischler in some papers that were written quite some time ago. I would apologize for talking about such old work at this conference, except it's clear that very few people read or refer to these papers. And so I'd like to tell you what I think is something very important. At the festival for David Gross's birthday, I called this set of ideas asymptotic darkness. It's really based, it's a conjecture, it's based on lots of older work, both in string theory and in classical general relativity, a rather incomplete reference list to that older work from which I think you can find most of the original references is given on that transparency over there. But the basic point is that the high energy behavior of quantum gravity is dominated by the creation of black holes. Scattering processes, if we tried to do the sorts of short distance measurements that determine the high energy behavior in quantum field theory, we find instead that we form black holes. The black holes are large. Short distance doesn't exist because of that. That's the ultraviolet cutoff of the theory. And this connection between high energy and large black holes is sort of the ultimate version of the ultraviolet infrared connection that we've talked about many times over the past few years in string theory. Now, when you talk about this conjecture, relativists say, yes, we knew that all the time. And string theorists say, well, you're going to high energy, what about alpha prime corrections? And one of the points of the paper that Willy and I wrote was that the relativists are right. That if this picture is verified in classical general relativity, then it's self-consistent. Because outside the horizon of this huge black hole, the curvature is very small. So the higher order terms in the alpha prime expansion of the effective action are just not relevant. And so very peculiarly, what we think of as the low energy effective action of the theory is actually telling us things about the very, very high energy behavior of the theory. But we really shouldn't be that surprised by that because we've learned so much about the UVIR connection. As a consequence of this, it's very much harder in a theory of quantum gravity to disentangle what you mean by the Hamiltonian and the vacuum state. This separation between ultraviolet and infrared that goes into that distinction in quantum field theory doesn't exist. So there are all sorts of other hints in classical gravity that this is the case. The fact that the Hamiltonian is defined by a surface integral at infinity. So this idea that you have a bulk Hamiltonian which determines how the system is behaving inside, and you twiddle something on the surface to put it into one of many different vacuum states, that can't make sense in general relativity because the whole Hamiltonian is defined on the surface. Again, this is a consequence of the existence of black holes, because given the fact that given enough energy you can make an arbitrarily large-sized black hole, there's no place else to put your variables for defining the Hamiltonian except on a surface at infinity. So at large Mandelstam invariance, scattering produces black holes. I emphasize again that basically all we have to do to prove this is to solve some hard problems in classical general relativity. And Steve Giddings and Doug Erdley have just made a big step in that direction. I think by now the problem is sort of reduced to proving cosmic censorship for a particular class of initial conditions. And once we've solved that problem in classical general relativity, it was solved in a positive sense in 2 + 1 dimensions by Matchell. Once we've solved that problem, we'll know that these ideas are basically correct. If scattering produces black holes, remember that the temperature of a black hole decay, can also be described, at least in a coarse-grained way, by semi-classical physics, as Stephen Hawking taught us. And the temperature of the black hole is extremely low if its mass is extremely large. And so very high energy scattering is very, very sensitive to the infrared details of what the low energy states are that the black hole can decay to at very low temperature. Again, the high energy part of the theory that gives its definition depends sensitively on what we usually think of as the vacuum. So I want to give you some examples of how you can use these ideas to understand again things that we've already learned. Just imagine that Juan Maldacena didn't exist, and that nobody had thought about the ADS-CFT correspondence, and Igor Klebanov also didn't exist. And here's a derivation, in quotes, of the ADS-CFT correspondence from the general principles of quantum mechanics and gravity, plus this principle of asymptotic darkness. You think about the quantum mechanics of an asymptotically anti-de Sitter space. You admit the fact that the high energy states, this is what was suggested in this paper with Aaroni, that the high energy states are in fact dominated by black holes. You believe, therefore, the Bekenstein-Hawking formula for the black hole entropy. And then you look at that formula, and you see that that formula looks like another system with the same symmetry group, namely a conformal field theory, but a conformal field theory in one less dimension, a conformal field theory that can be thought of as living on the boundary of the anti-de Sitter space. And you can see both the non-extensivity in the bulk of the entropy and the basic form of the spectrum. And given Wilson's definition of what a quantum field theory is, this almost tells you that asymptotically anti-de Sitter quantum gravity is a conformal field theory in d-1 dimensions. So now apply this principle to asymptotically flat spacetime, thinking about a time-like generator of the Poincare group as the energy operator. Then the density of states that's implied by this goes like the exponential of the energy to the d-1 over d-2 over d-3 power in d spacetime dimensions. And that, notice, is always blowing up faster than an exponential of the energy. As a consequence, the kinds of things we'd like to think about in quantum mechanics, the correlation functions of operators at fixed time in the vacuum state, are not distributions on a space of functions with compact support. In plain language, that means you can't really talk about operators at fixed time. You have to smear them out in some way with a particular exponential fall off in time that depends on what dimension you're in. And is determined by the black hole energy spectrum. Now, one way of looking at this is to say, yes, we think about Minkowski space as we do anti-de Sitter space, think about the conformal boundary. The theory that we might want to define lives on scri plus and scri minus. And if I do that, I can see there's no Hamiltonian version of the theory. There's no time evolution that you can define that makes any sense on scri plus and scri minus. You can see this just by thinking about the theory of massless particles described on scri plus and scri minus. The equations of motion are already solved. But there is another way to approach the dynamics of quantum mechanics in an asymptotically flat space-time, namely light cone physics. And in light cone physics, the Hamiltonian is P minus, sorry for being old-fashioned, goes like m squared over P plus, where m is the mass. And that means that the spectrum as a function of P minus is better behaved. You get an extra factor of a half in the exponent as a function of P minus. There's a 2 in the denominator in this formula here. And as a consequence of that, for every non-compact dimension greater than 4, light cone quantum mechanics behaves as we've always imagined quantum mechanics to behave, and has what might be a reasonable set of correlation functions at fixed light cone time. And we can imagine trying to do the conventional sorts of things that we do in quantum mechanics. And indeed, there are some models, the matrix theory versions, admittedly not really in asymptotically flat space-time, but only with discrete light cone quantization, that seem to describe things, but only in light cone time. By the way, I'd like to point out that d equals 4 is special from this point of view. In d equals 4, suddenly even the light cone Hamiltonian has a spectrum that grows exponentially with the energy. That's Hagedorn behavior, but not like the Hagedorn behavior of strings, which is exponential in a time-like generator, but the Hagedorn behavior in P minus. So even light cone Hamiltonian physics might not be well defined. And I believe that this pathology is probably connected with other things we know are wrong with four-dimensional space-time, namely the problem of infrared divergences, the non-existence of the S matrix, the fact that consequently you have to work with the Bondi-Metzner-Sachs group rather than the Poincaré group, and so on and so forth. It's 4 dimensions is going to be more complicated than any other dimension. And we're stuck. We happen to live in 4, so we're going to have to understand it. One final remark I'd like to make here is that even in quantum field theory, when I work in the light cone, a change of vacuum state is always implemented by changing the Hamiltonian. Now, in field theory, we think of this as a defect of light cone physics. But I want to suggest to you that given the context of these other ideas, that may be, again, another hint that what we've got is, in general, different Hamiltonians rather than different states of the same theory. So now let me come back to this other method of finding one vacuum inside another. Maybe there's still a way we couldn't do it by going and looking at the high energy behavior. What about forming bubbles? I dealt with this paper that I wrote a little while ago, and the bottom line is it doesn't work. If you try to make a bubble and you have some tension when you do this, always in the bubble wall, it costs you some energy to make this because in order to change from one vacuum to the other, you have to pay something in the bubble wall. And if that's the case, the mass of the bubble grows like the radius to the d minus 2 dimensions in d space-time dimensions. And so the Schwarzschild radius of the bubble inevitably gets larger than the bubble size. And so you can't make, in principle, bubbles of arbitrarily large size in the theory of quantum gravity. And if the tension, the barrier between domain walls is of order Planck scale, this maximal size for bubbles is of order Planck scale. And so it really doesn't make sense at all generically to think about bubbles. You can only think of them as asymptotic quantities, asymptotic things that might make sense in certain regions of moduli space, you might imagine that that allows you to connect different disconnected moduli spaces by sort of going down to extreme regions and connecting them together, as we saw in Shamit Katru's talk. But in fact, you're defeated because even along a moduli space, it turns out, that although you can make bubbles of a second vacuum inside the first one, you have to do it in a very, very intricate way, in such a way that if the distance in moduli space between the two vacua is d, then the size of the largest bubble you have to make in order to see vacuum number 1 inside of vacuum number 2 is exponentially growing with the distance in moduli space between them. And so there really is no way to get around this by going to extreme regions of moduli space. Now, the reason that bubbles exist in quantum field theory is really because in any quantum field theory, supersymmetric or not, if I make a big enough bubble so that it's exactly flat in the limit that its radius goes to infinity, it's a domain wall, and every time I have discretely separated vacua, there are topologically stable domain walls in quantum field theory. So another way of investigating these problems that I'm talking about is try to think about the cases that we know about in valid theories of quantum gravity where we can construct domain walls, and we do have those that have been discussed extensively over the last few years in the ADS-CFT story. And I'll hurry up now because I see my time is running out. But the basic idea here is that you can construct infinite BPS domain walls, but you can see from the physics of those that they don't really describe an interpolation between two different vacuum states, even though that's what it looks like from the point of view of low energy supergravity. And the reason is one of the most famous things in this discussion is the fact that the transition between these two ADS states in a BPS bubble is described by a renormalization group flow. The theory that you find on one end has a smaller entropy than the theory that you find on the other end. This is called the holographic C theorem, and it's supposed to be a general, a specific version of the general phenomenon that when you do renormalization group flow, you lose degrees of freedom. That's not what happens in quantum field theory when you have a domain wall separating two vacuum states. The two states on either side of the domain wall have exactly the same high energy behavior, exactly the same entropy. This is not true here. It shows us that these domain walls are not separating two vacuum states, but really separating two different Hamiltonians. So my conclusion from this is that there are many anti-de Sitter quantum gravity Hamiltonians, that the cosmological constant that appears in those Hamiltonians is a discrete and tunable parameter which controls the high energy density of states, and that I shouldn't believe the naive extrapolation of the classical Lagrangian picture which tells me that these are different vacua of the same state, of the same Hamiltonian, excuse me. Now, where does this leave string theory? I think what it shows us is that we have at least a finite number, I suspect actually an infinite number, of exactly supersymmetric Hamiltonians for quantum gravity with asymptotically Minkowski or anti-de Sitter space of various dimensions. They're different Hamiltonians. There are probably also stable non-supersymmetric states, as described in the work of Giddings, Katru, and Polchinski and Eva Silverstein. And I think that the only way we're going to resolve the problem, you know, you've got a lot of Hamiltonians, why does one particular one describe the real world, is by admitting that the real world is not described by any of them. And I've suggested that instead it's described by a large de Sitter space, where again the cosmological constant, this time positive, is a discrete tunable parameter that determines the number of states at high energy, the ultraviolet, or what is the same thing, the infrared cutoff. Now this may imply, I've argued that this implies that as I take the lambda goes to 0 limit, lambda is now a tunable parameter at my disposal, that I actually have to approach an isolated n equals 1, d equals 4 supersymmetric Hamiltonian, which is the kind of thing that we've been trying to construct in string theory. Recently, there are some papers that, in my mind, throw some doubt on my arguments, and I've been thinking about this very hard. I don't have anything to report to you about these papers, but I hope to fairly soon in the future. And so what I think is going to happen is that we're going to find a theory of de Sitter space, which, when lambda goes to 0, approaches one particular, or maybe we'll be unlucky and we'll find that there's a discrete set of exactly supersymmetric Poincare invariant n equals 1, d equals 4 Hamiltonians that describe string theory. That string theory will give us some of the properties of the real world, things like the gauge group and its representations. But they won't tell us everything. They won't tell us, in particular, about supersymmetry breaking. So the problem for string theory has not really changed. It's still find solutions of some equation W equals covariant derivative of W equals 0. Now, given that I've been trying to throw doubt on the idea of an effective potential, you may think I'm being inconsistent by suggesting that there's such a thing as an effective superpotential that we could write down and find solutions of in this way. And I think that may not be true. And the reason for this is that if I go out to the asymptotic regions of moduli space, the notion of potential and superpotential does make sense. And I can calculate terms in an asymptotic expansion around those asymptotic regions. And W, as opposed to any of the other things in the theory, is holomorphic. And we actually expect that expansion to converge and to define in a unique way a function that we can analytically continue. If the moduli space is not a manifold, as we expect from the story of n equals 2 compactifications, we may need a variety of different asymptotic expansions to calculate it. But I still think that this is probably a well-defined mathematical problem. It has a very topological flavor. And you've heard from Mike Douglas at some of the ways one might go about trying to solve it. And so on that, I hope, optimistic note, I'll shut up.
Questions?
In what sense are the different supersymmetric vacua different manifestations of the same thing?
Well, I think that there's a set of rules that follow from supersymmetry and the principles of quantum mechanics, and I think they'll all obey those rules. But I think that except for the fact that in many cases we have moduli and we can sort of extrapolate to regions where they do look like something similar, what we're really doing when we do that is throwing away lots of degrees of freedom that make them different and going to non-compact regions of moduli space where things decouple. And in that way, we can see that there are relations between them. And I think that that's a lot of what we've done over the last few years. For discrete, isolated, n equals 1, I think they obey the same general principles, but if there are multiple copies, I don't think they're really connected to each other.
Other questions?
They're sometimes connected even in low energy field theory, even if there's a barrier. Like different bundles, where just in the space of gauge fields. It sometimes happens that there are different vacua that can't be connected through solutions, but can be connected through a barrier in field space. Perhaps even in low energy field theory, or perhaps, as we've heard from some speakers, by using branes as domain walls.
Right. As I tried to explain, I think that those notions are only approximate and that there's no exact way in which those things can really be connected. You can't make a precise calculation of the properties of one theory based on the other.
But don't you, isn't that evidence isn't that evidence that in some sense there are manifestations of the same thing, even if it can't be construed as literally, as in some framework you presented at the beginning for how to regard the two things as manifestations of the same thing? That's why I asked you for your view of in what sense they were manifestations of the same thing.
I think I gave you my view. I think that there are limits in which they can be related to each other.
I wanted to ask how certain you are that that in a theory of extended objects, high energy scattering always creates black holes. You know, one effect that you might worry about is that the extended objects themselves grow with energy. For instance, strings at energy E grow like E, whereas black holes grow only like e to the power 1 over d minus 3. And that effect might naively invalidate the prediction that high energy scattering gives you black holes always.
Yeah, this is certainly a conjecture. However, I think that what we've learned, particularly from the work of is this on? I'll just shout. I think what we've learned, particularly from the work of Amati, Ciappelloni, and Veneziano, is that when you try to extrapolate string calculations of scattering amplitudes into the regime where you expect black holes to be formed, you see string perturbation theory breaking down in an unambiguous way. And there's work of Horowitz and Polchinski that suggests that there's this transition regime in which high energy strings collapse and become black holes. So at very high energy, it's clear that we have much more entropy in black hole states. And if you just let the system wander over its energy surface, it's going to want to form black holes rather than anything else.
More questions?
You seem to imply that even though in the interior of moduli space, this notion that different points are just vacuum of the same Hamiltonian doesn't work. You implied that if you went out towards the boundary of moduli space where things were becoming non-compact, that it did work. And could you explain that? I didn't see where your arguments break down.
No, they don't break down. They just have limits, okay? So the question is the degree of precision in which you can, in one vacuum state, recover the physics of the other. In order to be extremely precise, you have to make extremely large bubbles. You can only do that in these cases separated by walls by going far out into moduli space. In that limit, you can make a bubble as large as you like by going far enough out in moduli space where the barrier goes down. But then if you want to get back to the interior, you run into this problem that the bubble size grows exponentially with the distance that you have to go in moduli space. And so there's no way by going down to the asymptotic regime that you can sort of come around and skirt around the low edge of the barrier and connect the two. And again, the thing I want to be very precise about is I'm asking you to reproduce precisely or with any required degree of precision the physics of one vacuum by experiments done in the other.
More questions? If not, we thank the speaker again.